start recording and share my screen. Okay, where's the PDF? This one. All right. So today is going to be our second lesson on operations on functions, right? So last class we reviewed the basic operations. Those are like very basic. You need to know them when you're graphing. They're very important. So make sure you know those. We will review them briefly today, but not that much because we are going to learn some new material today called the compositions of functions, which is also very important. So make sure you're listening and taking notes. So let's begin with the homework questions, which I assigned last week. And I'm just going to call up some volunteers afterwards to help us solve these. Okay, so I'll give you a few moments to put your answers in, and then I'll just call up some volunteers. Well, actually, you can't really put in your answers. Just like write them down on a notebook or rethink them. I'll give you a few moments to do that. All right, let's see. So, do we have any volunteers who can help us graph this? All right. All right, William, very good. Okay, so let's see here. Graph f of x is equal to the square root of 1/2 of x minus 3.
So basically the parent function is the square root. So it's like that. It's basically like that line, and because there's a negative 3, we have to move down 3.
All right, hold up. So is moving down the first thing you did?
Oh wait, never mind. Actually, we had to first like compress it.
Yeah, very good. You have to do the stuff inside the parentheses or whatever. Like for example, if you have f of x and you turn that into f of 2x, minus 3, you don't do this first. You have to do the stuff inside the parentheses first, right? So you got to do the stuff inside the square root first, right? So very good. All right, continue.
Yeah, after compressing, we had to like I'm not sure, like we had to like kind of expand it vertically.
Yeah, so this is like values for the original graph. It's 1 1 and then 4 2 and then 9 3, right? So if you actually you don't compress it, right? Because if you look at the domain, it actually is stretched. So instead of having like 1 1, we're gonna have 2 1 and 1 2 3 4 5 6 7 8. We're gonna have 8 2, right? We're gonna stretch it horizontally like this. You agree, right?
Yeah, and after that, the tree over there, we had to like kind of move it up vertically, like stretch, or I mean, no, compress it.
Are you sure about compressing? When it's
Wait, no, no, no.
vertical, there's no, that's directly affecting the y, right? There is no domain value. So you just directly multiply the y values by 3. Look. So this 1 here becomes a 3 here, and this 2 becomes a 6, right? This. So it's more like this now, right?
Yeah, and then
Okay. Then,
after that, then we move down three.
right. So then should be equal to about here, and this should be equal to here, right? Out here. So then you just move it down, right? It's more like this. Okay, now my points aren't like exactly accurate, but that's what it should have looked like, all right? After you're done with all of these transformations. All right, very good, William. The only problem is that you need to look at the order of your transformations, right? Let's just review the order, right? So first we need to do the stuff inside the parentheses. Then you need to do what's multiplying the parentheses, and finally moving down or up is last. All right, we can save that for later. Right, so let's continue the second problem. Graph f of x is equal to the square root of negative x plus 3 plus 1. All right, I'll give you a couple moments to do this. All right, let's do this one. So graph square root of negative x plus 3 plus 1. So for this one, right, we need to do the stuff inside the square root first. So the parent graph is going to be the same. It's going to be y is equal to the square root of x. Looks like this, right? Okay, then I'll make this a little bit bigger. So what you need to do is you need to do these horizontal shifts first. So it's going to look like something like this. And the tricky part about this is that you reflect after you do these shifts. So it's gonna, why did I erase that? Let's go back. Okay. Now, so after you shift, then you're gonna reflect. So then it's gonna go like this, right? Because a lot of people, right, make mistakes. They reflect first and then they shift. Then it's gonna look like this, which isn't correct. All right, so you gotta move. All right, horizontal shifts before you reflect or anything. Okay, so then it's look like that. All right, then you add 1 to it. So then it's just gonna look like this, right? All right, very easy. Now let's do this. Let's find a volunteer who can do this. How about Kaylee? Kaylee, would you like to volunteer?
So f negative 1 is equal to 2. Y equals 1/3 f negative 1 minus 1. Equals 1/3 times 2 minus 1 equals 2/3. Subtract 1. And that is equal to negative 1/3.
All right, good.
2x plus 5 is equal to negative 1. 2x is equal to negative 6, so x is equal to negative 3.
Very good. So then it's gonna be -3 and -1/3. Great. Good job. All right. So use my method, which is very nice. Okay, so if you had done this any other method, for example, transforming it with all those transforming the point directly, that would have been very tedious, right? So you have to use this method to make it faster. Very good. So let's just review some transformations, right? So what is this? Y is equal to fx plus a. So this is just a vertical shift because it's directly affecting this y value, right? Directly affecting this. Okay, so then so let's say we have our example graph. This is 0, this is 4. All right. And if you add 1 to it, f of x plus 1, then it's just going to add a 1 to it, right? Add 1, something like this. Okay. It's gonna shift it higher, right? Okay. And if you subtract 1, it's gonna look like this. Just shifted downwards, right? So it's something like that. Actually, I shouldn't use a dashed line like this. This isn't good. What I'm gonna do, I'm gonna change the color, make it clearer, you know. All right, so this 0, 4. Let's make this red or orange. Is that orange? Yeah. Okay, that's right. Anyways, something like this. All right, that's not the best graph, but it'll do. All right, make this green, right? Something like this. If you subtract something. Okay. So from this, we can tell that if a is greater than 0, so if it's positive, then we're going to shift up. All right, this is a vertical shift, right? And then we can also tell that if a is less than 0, all right, we're going to shift down. And of course, if a is 0, nothing happens because it just all cancels out and there's nothing, right? So basically, negative, it's down, positive, it's up. It's quite self-explanatory, right? It's what you would expect it to be, right? You don't expect it to like be positive and shift down, right? You don't expect it if it's negative, it shifts up, right? You don't expect that. It's very self-explanatory. This is pretty good, right? So this next one is a bit tricky, right? A lot of people make mistakes on this because they think that if x is subtracting something, then we have to move left, right? And if x is like adding something, we have to move right, right? It's what we would expect, right? If it's positive, it corresponds to the right. If it's negative, it corresponds to the left, right? It's pretty self-explanatory. It's what we expect because that's how a number line works, right? But this is not the case because of the domain, all right? All right, pay attention to the domain. So this is our example graph here from 0 to 4, right? So the domain is 0 to 4. And let's say we had f of x minus 1. What you got to do is you got to take this stuff in the parentheses, right? And set that and put that in the domain. And then if you put that in the domain, then you can finally see what are the effects on the domain, right? You solve for x here, this new domain would be equal to 1 to 5. So if you're subtracting something, you are actually moving to the right. Something like that. Right? Now if you do f of x x plus 1, then you put that in the domain, right? It's going to be equal to negative 1 to 3, right? So you can see you're actually shifting it left this time. Something like this. Okay? So do not fall for this misconception that if it's negative, then we have to move left. Right? You got to look at the domain for this one. So if a is positive, as in we are subtracting a because there's a subtraction here. If you're subtracting a and a is positive, move right. A is negative, move left. All right, so you might be confused by this. Didn't you just say that if it's positive, it should move left, right? But you see there's a subtraction sign here. Okay, so now let's move on to the shrinks and the compressions, right? So this one, just like the first rigid transformation, is very self-explanatory because it's not affecting the x, it's effect on the y. So it does what you would expect, right? It does what you would expect. This is our example graph, right? So when you multiply c to it, all right, if c is greater than 1, for example, you will have c 2f of x, it would do this, right? It would do this. It would stretch the graph, right? Okay, it stretched the graph, something like that. Okay. If it's like 1/2 of f of x, it would shrink the graph by a factor of 2. Okay, something like that. Just divide all the y values by 2, right? It's very self-explanatory. It would be, it's what you expect. So from this, we can say that if c is greater than 1, what you're going to do is you're going to stretch, right, by a factor of c, right? Okay, if c is, well, actually, if c is a fraction that's not 0, and of course it's less than 1, it's a fraction, you're going to shrink it or compress it by a factor of c, right? Okay, and of course if it's just 1, nothing happens because it's the same thing, right? So now this is another tricky one because it's complete opposite of this. It's again effect on the domain. All right, key point is effect on the domain. You have to look at the domain, right? So our example graph. Let's just make one of these. All right. Okay. So if we have f of 2x, actually what you're going to do is you're going to, contrary to what you would expect, you're actually going to shrink it. All right, because the last stretch slash compression, if it's multiplied to f of x, you'd actually stretch the graph vertically. But this time, if it's if c is greater than 1, you actually compress it because of this domain. So let's look at the domain f of 2x, and you see, put that into the domain. So for x, you can see that it's actually, you actually shrink the domain like so, and then the resulting graph would be something like this because you divided it by 2. Okay, and then if we take a look at f of 1/2 of x, you see here, put that into the domain, x is going to be equal to this 8, right? So then my graph is going to run off the side, but it's going to look like this, right? It's stretched. Okay, and from this we can conclude that if c is greater than 1, you're going to shrink by a factor of c. Of course, it's horizontally. If c is a is non-zero, right? Greater than 0, less than 1. Why do I keep doing that? Then you're going to stretch by a factor of c. Okay, that's basically it for the material we learned. Okay, pretty basic stuff, right? Nothing too hard. It's very after you know it, it's pretty easy to rederive it. Okay, so of course we also learned about some new operations, right? These are not your like usual ones. You won't do too much with them. I just want you guys to know it. So of course we have our trusty, this example graph here. It's 0 to 4. Now, what happens when you have when the y value is the absolute value of x? That means the y value has to be greater than or equal to 0, right? So then you can see that our new graph should only be greater than or equal to 0. So all those negative parts of y are actually rebounded up into something like the McDonald's logo. Look at this. All right, anyways. So basically, y cannot be negative. It can only be positive, so all negative values are rebounded up, right? If you had a parabola like this, then it will turn into something like this, right? Now we have this other thing, and we got to look at it, of course, put it into the domain. If you solve this, all right, if you solve this, you can see that's going to be negative 4 2x. I'm just going to skip all the calculations now. It's very easy. I've taught you guys this with the absolute value inequalities. You can go solve it yourself if you want to. But this is what you get after you're done solving everything, getting rid of the absolute value. It's going to be from negative 4 to 4. That's the new domain. And you can see it's just reflected across the y-axis. But you keep the old one there, so it looks like a mustache now. Right. That does look like a mustache. Anyways, moving on. We have our new material finally. Okay, so now we're going to be working not just with one function, but with two functions. Okay, so let's say that you're adding two functions, right? That's f plus g of x, right? These are very self-explanatory. All right. That's just equal to f plus f of x plus g of x. You get the trend, right? All right, so let's call up some volunteers. Let's see who can help us. How about William? Okay, William, just do this very quick. So following this trend, what would f of x minus, f minus g of x equal to?
Probably it will be f of x minus g of x.
Very good, very self-explanatory. What about this?
Basically it's f of x times g of x.
Great. All right, now how about this?
F of x divided by g of x.
All right, any restrictions?
Yeah, g of x cannot be 0.
Great. G of x not be equal to 0. Good. All right, so that is the only restriction in all of these, and that's about it. Except for actually, let's find the domain of these. Actually, yes. I almost forget about that. Okay, so let's say that yeah, let's just go and find the domain. All right, so what do you think is the domain of this, William?
The domain.
Yeah, the domain of it. In terms of the
Uh,
domain of f and in terms of domain of the g. Would it be like the domain of f union the domain of g, or would it be like the domain of f intersection with the domain of g?
maybe it's intersection.
Great. It's intersection with the domain. Actually, let me do this clearly. Domain of f intersection of the domain of g. And what about f minus g of x?
Maybe still intersect.
Great. And also f times g of x.
Also intersect.
Okay, so very good. So that's the domain for f plus g, f minus g, and f times g. And that's the same case for f divided by g, except what?
G can't be 0.
Great. So for this one especially, it's going to be domain of f, intersection of g, and g of x cannot be equal to 0. Great.
Okay.
Very nice. All right. Good job. So now let's learn about the composition of functions. All right, this is very, very easy. Now, we're not going to talk about the domain of this yet. All right. We're not going to talk about the domain of the composition of this yet. right? Because it's a little bit more complicated than what we did back there. Okay, so let's just learn just how to compose functions, right? So let's say let me just come up with an example, right? So f of x, now let's just switch back to blue, you know? All right, so f of x is equal to x squared. All right, correct. Now, let's say, William, what would f of 2x be equal to?
F of 2x.
It's not that hard.
Maybe it's x to the power 2 over 2.
X to the power of 2 over 2. That's incorrect. It's
Uh,
very simple. It's very simple. Get the correspondence.
oh wait, maybe it's first do x divided by 2, then to the power 2.
Okay, William. So what you need to do is it's you just plug it into the same thing, right? Right? Because if f of
Uh,
x is equal to x squared, right, then f of 2x is just equal to 2x squared, right?
oh,
Then
I
what is f of what is f of 3x then?
then it is 3x squared.
Yeah, it's just 3x squared, right? You just plug it in for x, right? So then f of a is equal to a squared. F of t is equal to t squared. So what you can do is you can just put random stuff in for x, right? X is a variable. It's not like always x, right? It's not like a temp. It's just a temporary thing, right? Okay, it's a variable. You can change. So what if our variable was an entire function? That's called the composition of functions, right? So this is f of g. You pronounce this f of g, not fog, right? I don't want to hear anybody pronouncing a fog or golf. All right, this is f of g and g of f. Okay, so f of g is basically just equal to f of g of x, right? F of g of x. And what you need to do is you need to put the entire function inside the f function as an input. For example, let's say g of x was equal to 2x and f of x was equal to x. Then x squared, f of g of x is going to be equal to f of, you're going to put the g of x function inside the f of x function. So what is this? It's just going to be equal to f of 2x, which is equal to f of not f of anything. It's just 2x squared, right? You're going to put the entire g function in as an input for f. Now, if you change this up, right? Let's say g of x wasn't that. What if it's x cubed, right? Doesn't matter. It's just f of x cubed now, which is equal to x cubed squared, which is x to the 6th. All right, but we'll learn about exponents later. Okay. So you're just going to put the entire g function in for f. Now, if it's g of f, it's the order is switched, right? Okay. So instead of that, then g of f of x is just going to be equal to g of x squared, which is equal to x squared cubed, right? Okay, and compositions are not always the same. In this case, they are the same. Like, for example, g of f, f of g are the same, right? But they're not always the same, okay? All right, for example, if you had x squared and square root of x, it wouldn't be the same, right? Actually, would it? No, it wouldn't. Actually, it's very close, but it still wouldn't. Okay, let me think of a better example. How about so if you had like 2x plus 3, and then, for example, you had the square root of x, of course, it wouldn't be the same, right? Because they're so different, right? But in this case, the functions are kind of similar, so that's why they're the same. So don't expect f of g and g of f always being the same. Okay, so let's do some practice problems, all right? So I'll just give you a few moments, all right, because you're finding a lot of stuff here, so I'm just going to give you a couple minutes to do this, all right? And then we will regroup and solve this together. All right. So let's see. Okay. Let's look. All right. So let's do this. S plus G is very easy. All right. You just add the two functions. Actually, it's not that hard in the first place. Right? You just add them. F minus G is also very easy. Okay, I forgot. This is G of X, by the way. This is G of X. Did I make the same mistake? I made the same mistake. And that's G of X. That's G of X. Okay. All right. Then it's not the same, actually. Okay. Then it's going to be x plus 2 minus 3x squared, right? Fg is going to be equal to this, right? And of course, then f divided by g is going to be equal to x square root of x plus 2 over 3x squared. Now, our next one is to find the domain, right? So let me just copy these down real quick. All right. Uh, all right. I copied down the answers for these. Now you just got to find the domains of them, okay? All right, let's start. Okay, so the domain is just the domain intersection of these two functions. As you see, there's no domain restrictions on G, but there is a domain restriction, and that is that X has to be greater than -2, because X plus 2 has to be greater than or equal to 0, right? Or the square root is undefined. Right? So you see here, the only restrictions here is that here X has to be greater than the domain here is just going to be equal to -2 to infinity. Here it's also -2 to infinity and -2 to infinity. But you see here, f over gx cannot be equal to 0 because of this domain restriction. So then we have to skip 0 like so. All right, and that's about it for finding the domain. Pretty easy. And finally, to try this, we have f of g, which we just plug in g for x in the equation, which is going to look like this. And for g of f, we do it similarly. And very nice, we got rid of the square root. So it's basically now just this is equal to 3x plus 6. Very nice. All right. So that's about it for this lesson. All right. Thank you for listening. And I'll see you guys next, well, the week after next week. Because next week we don't have any class. All right. So make sure you remember. And all right. Bye.
Bye. Happy
Bye,
Thanksgiving,
thank you.
Mika.
Bye, thank you.